Here we are going to solve an example of radioactive decay. So the isotope cobalt-57 decays by electron capture to another isotope, iron-57, with a half-life of 272 days. So the daughter nucleus iron-57 is produced in an excited state and it emits gamma rays that can be detected. So we are to find the decay constant, and next we will solve if the activity of cobalt-57 is 2 microcuries. So how many nuclei does it contain? So we will be solving two things. First, the decay constant, and then the number of nuclei given the activity. So first we will solve for the decay constant. Since the half-life is given as the number of days, we will first convert it to seconds. So the half-life is 272 days, and 1 day is 86,400 seconds. So multiplying these two, we will get 2.35 times 10 to the 7 seconds. And next, we can now solve for the decay constant. So the decay constant is related to the half-life by this equation. So T sub 1/2, or the half-life, is equal to natural log of 2 over the decay constant. So we can solve for the decay constant, which is, we divide ln of 2 by 2.35 times 10 to the 7 seconds. So performing the calculation, we can get that the decay constant is 2.95 times 10 to the minus 8 per second. So this is the answer to the first question. So next, given that the activity is 2 microcuries, how many nuclei does it contain? So first, let us discuss what is the unit. What does the unit of curies mean? So the unit of curie is used for quantifying radioactive decay. So it has units of number of decays per second. So 1 curie is equal to 3.7 times 10 raised to 10 decays per second. Or you can also say that 1 decay per second is equal to 1 becquerel. And then if 1 decay per second is 1 becquerel, then 1 curie is equal to 3.7 times 10 to the 10 becquerels. So 1 decay per second is equal to 1 becquerel. So the unit for the symbol for curie is Ci, and for becquerel is BQ. So 1 curie is roughly the amount of decays that happen in 1 gram of radium. So it was credited for the scientist who discovered radioactive decay, perhaps. So that scientist is Marie Curie. So she was studying radium and how does radium emit radioactive decays. So given that the activity of cobalt 57 is 2 microcuries, how many nuclei does it contain? So we go back to our definition of radioactive decay, wherein the decay rate or the time derivative of the amount of nuclei is proportional to the amount of nuclei, the current amount of nuclei. So we can also write this as dn of t dt equals some proportionality constant times amount of nuclei. And this proportionality constant is what we have solved earlier, which is the decay constant. So given that we know the decay constant and we know the current decay rate, we can solve for the amount of nuclei present. So we have for the decay rate, the value for the decay rate is 2 microcuries, 2 times 10 to the minus 6 decays per second. And for our decay constant, we have let's write it this way. So we have n equals minus dn of t dt all over the decay constant. So here we have 2 times 10 per second over our decay constant is 2.95 times 10 to the minus 8. 2.95. Decays per second. So we have, solving this equation, we will have about 2.51 times 10 to the 12. So seconds will cancel out here. This is per second. This is per second. So what will be left is decays. So you can also think of this decays as equivalent to the number of nuclei, because we quantify decays by number of nuclei. So we can also say that this is number of nuclei or nuclei. So this is the answer for the second question. So given that the decay rate is 2 microcuries, the amount of nuclei is this number, 2.51 times 10 to the 12 nuclei. So to add another question, to know more about activity, there's another question. So what is its activity after 1 year? So we go back to the equation where n of t equals n naught and e to the minus lambda t. But we know that this n of t is, or rather, minus t n of t dt is equal to minus lambda n of t. So we can write this expression as just to remove the derivative. So we can write this as a of t, which is the variable for activity. So activity as a function of time is equal to some proportionality constant times n of t. So let's express n of t as, so a of t over minus lambda. So let's put this back in this equation. So we have a of t over minus lambda equals n naught e to the minus lambda t. But we also know that at n naught, at this value of n naught, we have a corresponding initial activity. So we can also say that n naught is equal to some initial activity over minus lambda. So we will replace n naught by this one. So we have a of t over minus lambda equals a naught over minus lambda e to the minus lambda t. And then minus lambda cancels out. So we have an expression for the activity as also an exponential decay. So this equation is similar to n of t. So we can use this to solve for the activity, how many curies or how many becquerels, as a function of time. So let's solve this. So a of t, or rather a of 1 year, what is the activity after 1 year, equals, it is equal to the initial activity times e to the minus lambda of 1 year. So 1 year is in seconds equal to 3.156 times 10 to the 7 seconds. So a of, let's just write as a of t, it's equal to a naught. So what is a naught? A naught is the initial activity which is given in the problem, which is 2 microcuries. So 2 times 10 to the minus 6 curies times e raised to minus decay rate is decay rate 2.95 times 10 to the minus 8 times 1 year, 3.156 times 10 to the 7 seconds. So this value amounts to about 0.394. So 0.394 times the original activity, which is 2 microcuries. So this means that there will be 0.394 of the original activity after 1 year. So after 1 year, we have this value, 0.788 microcuries. So not only that the amount of nuclei has decayed, also the the activity has reduced to 0.788 microcuries.